So good evening, I'm Calvin Joseph, and today I'm going to conduct the week 4 problem solving and doubt clearing session for the course Control and Tuning Methods in Switch Mode Power Converters. So this is the outline which we will see today. We will be discussing about fixed frequency modulation. What are the techniques which we have seen before? Then what are the limitations of fixed frequency control, and why do we go for variable frequency control? In variable frequency control, there are basically three main kinds of control techniques. One is the constant on-time control, one is the constant off-time control, another is hysteresis control. So these things are there. We will also discuss about converter losses and certain light load control techniques. So start with week 4. So there is fixed frequency control. So what are the two types of control techniques which are there, which you all know? Two main control techniques which are there.
Fixed frequency and variable frequency.
Okay, fixed frequency and variable frequency are there, but in fixed frequency also two techniques are there, right?
Pulse width modulation.
Pulse width modulation is there. So one is like voltage mode control we have, and one is current mode control we have. These are the two main control techniques which we have. So in voltage mode control, what do? We have a sawtooth. This is there. And we compare it with some RAM. And this will generate our gate signal. This will generate our gate signal. Okay. So if you will see in this technique, in this part, it is always turned on at 0T and then at 2T. It is always turned on there. So the rising edge is fixed. The rising edge is fixed. But what changes is what is changing is this is changing. This is changing. So the rising edge is fixed, but the falling edge is changing. So that is why it is known as trailing edge modulation. Trailing edge modulation. This is because the instant of it being turned on, main control signal being turned on is same. But when it is turned off, this part, this can get adjusted. This can turn off earlier, this can turn off later, anything, depending on your control. So that's why this is known as trailing edge modulation. So now we'll consider the case of peak current mode control. So what do we have in peak current mode control? We have our main reference. Okay. And this is our current. Our current will fall, rise, fall, rise, fall. Okay. So over here at this point, what do we have? We have what is known as a set pulse will come. Periodic set pulse is coming. Okay. Sorry. So this is coming at 0T, 2T. These are known as your set pulses. Okay. And the instant at which it touches this instant, you have your reset pulses. You have your reset pulses. So these are your reset pulses. Okay. So then finally your gate signal which is generated is when your set pulse comes, it turns high. When your reset pulse comes, it turns off. Your set pulse comes, it turns on. Your reset pulse comes, it turns off. Like this, it will continue. So this is your main gate signal. This is true for buck boost, non-inverting buck boost. It's the same. You have, so this Q is your main control signal, which goes to your main control switch. And you have a set pulse, which is coming at periodic intervals of 0, T, 2T, etc. Your reset pulse gets changed by your reference. If your reference is lower, reset pulse may come faster. If your duty is different, etc., it gets changed. So effectively, what is changing? This is changing. It can turn off like this also. It can turn on like this also. Anyway, it can happen. So the falling edge is being modulated. That's why this also is trailing edge modulation. Okay, that's why this also is trailing edge modulation. Okay, so this is for peak current mode control. So is there any other technique which sir has taught about for fixed frequency?
Valley current.
Okay, acha. And Divya Sharma, like what issue are you facing? Because acha, she can't hear also. Okay. Now, sir has taught also what is known as valley current mode control. Okay, does this peak current mode control have any issue? Have any problems or difficulties? Or is it perfectly fine?
During a step up transient,
Mm-hmm.
the
Okay, peak current mode control has some structural instability, or like it can have some subharmonics. Subharmonics when D is greater than 0.5. In this case, what happens is your current will look like this. Suppose it goes here. Okay, this is anyway D greater than 0.5. You go here, just 1 minute. Ah, sorry. Okay. So it has some subharmonic instability, which we will see like it will look like this. It would rise, it would fall, it would rise, it would fall further. So this we'll see in the simulation. So it can be mathematically derived also that when your D is greater than 0.5, you will have subharmonics. And when you have subharmonics, what would be required? You have to use ramp compensation. You have to use ramp compensation. Okay. So this is for peak current mode control. Similarly, you can have valley current mode control, which is given over here. This is valley current mode control, in which what do you have? You have some valley current reference. Your current will hit here, then it will turn on, hit here, then it will turn on. And at periodic intervals, it will turn off. Okay. So over here, you will have your reset pulse. Again, over here, you will have a reset pulse. So this comes at T, 2T, etc. This is known as your reset pulse. Your set pulse will come whenever it touches the value. Over here, it will come. Similarly, over here, it will come, and so on. So this is known as your set. So your gate signal which you generate will be given like this. Go high here, fall here. Go high here, fall here. So this is fixed. This will happen at T, it will happen at 2T. This is fixed. But this is controlled. That when it will turn on, that comes from this event, when it will touch the valley. Okay, that is why it is known as valley current mode control. So when it touches the valley, at those instants only, you will have these rising edges. Okay, that is why uh, this is known as leading edge modulation. Okay, because when it will turn on, that will adjust. If your current which was there, if it touched over here, then what will happen? Your pulse would have changed like this over here. It would have turned on over here. So this rising edge is modulated, it is controlled. That is why it is known as leading edge modulation. Okay. Acha. So Divya Sharma, you're facing any issues or you're able to hear and able to see the screen? Okay. Okay, fine. No reply. Okay, so any doubts till this part? Any queries? Okay. So there are other control techniques as well. So now we will go to the variable frequency thing. And I'd like to point out that valley current mode control also has the subharmonic instability. For it has it for D less than 0.5. For D less than 0.5, it is unstable. Okay, for D less than 0.5, valley current mode control is unstable. Okay. Now let us go for another technique, variable frequency one, which is your constant off time control. So what happens in constant off time control is, it again you have your peak reference. This is your I peak reference. Okay. Your current signal, assume it touches over here. Then it will be off for one fixed time. It will be off for this fixed time. Then again it will rise, and when it touches that peak, again it will be off for a fixed time. Okay. So this is the fixed time for which it is off. Right? And then again it will rise. So this is repeated again. So this comes using a monoshot timer. This is your output of your monoshot timer. Okay. And your actual gate signal, which will be going to your switch, will be given like this. This is your actual gate signal. It is a complement of this. Not exactly the complement. There will be some dead time, everything. But this is your actual gate signal through. So constant off time control, this is analogous to peak current mode control. Okay. So let me repeat again for you guys to understand better. So you have a constant off time. Your off time is fixed. So, and when do you know that you have your fixed off time is when your current will reach the peak. When your current reaches its peak, then your current will start falling when your switch is turned off. So that amount of time for when it will fall, that is fixed. The T off is fixed. Okay. Then once T off is elapsed. Once this finishes, once it falls, then there will be an edge. Then your gate signal will go high. Current will again start rising. It will again start rising. And when it again touches the peak, then this will get triggered and this will turn on. This will turn on. And that time your gate signal also will turn off. And this monoshot timer output will be on for a fixed time of T off. That time your gate signal will remain off. Okay, so this is the logic for constant off time control. But the issue with this is your switching frequency is not fixed. When you have this constant off time control. Okay. Any doubts still here?
No, sir.
Okay. The next page. So next we have constant on time control. Constant on time control is similar to valley current mode control. Okay. Where we again have this valley reference. Your current falls. The current falls, then it turns on for a fixed time. It turns on for a fixed time, T on. Okay. Till that time your current is on, then it will turn off, turn off, turn off until it touches this valley point. Then again, what will happen? Your monoshot timer will rise, will remain on for this fixed time T on, for which your current will again rise. Once the time is over, it will fall. Okay, so this is how constant on time control looks like. And your gate signal also will be like this. This is your gate signal Q. And this is the output of your monoshot. So what happens over here is when the current touches the valley, then it will send an edge. And your monoshot timer will be on for this fixed duration of T on. Your gate signal also is on for that fixed duration of T on. After that is elapsed, then your T on, there's a falling edge. Okay. So your current starts falling because your Q remains off. And then when it again touches the valley, again you have a rising edge. Your monoshot timer is on, your gate signal also is on. And so on. It will be on for the fixed duration T on, which is fixed because this is constant on time control. And then again it turns off. Okay, so this is the logic of constant on time control because it is similar to valley current mode control and it has various benefits. Constant on time control is widely used for light load applications. For light load applications, which we will touch in a few moments, we will discuss about light load as well. Why, what is light load and why it is important. Okay. So next we will think about also, since this is valley current mode control, it is a type of leading edge modulation. It's a type of leading edge modulation. Okay. Because when this is turned on, like when this switch turns on, this is controlled. This depends on this instant. So that turning on, rising on, that leading edge, that is being the one which is controlled. That is the one being modulated. So that's why this is also, this is known as, this is a type of leading edge modulation. Okay. So now we have seen these type of techniques. There are two variable frequency control techniques we have seen. We have seen two fixed frequency control techniques. Now we will consider what is a technique which is known as hysteresis current mode control. So can anyone tell me what is hysteresis? Anyone has any idea what is it? Does hysteresis exist practically or not?
there will be an upper limit and lower limit. Within those two bounds, this current will be varying, inductor current.
Okay. That's right. So what happens in hysteresis current mode control is, sorry, we have a peak, we have a valley. Okay. In between this, your current will rise, fall, rise, fall, rise, fall. Okay. So at this instant, your gate signal goes high. When it touches this, your gate signal goes low. Touches here, it goes high. Again, when it touches here, it goes low. Similarly, it happens like this as well. So this is your gate signal Q. Okay, this is the gate signal Q. So there is no, fixed, nothing is fixed. Like your on time also varies, your off time also varies. Like in the previous techniques, what we had was either the switching frequency time is fixed, or either the T on time is fixed, or either the T off time is fixed. But in hysteresis current mode control, none of them is fixed. Okay. So this is also known as your band. This is your delta IH band. And ideally your delta IH should be equal to delta IL, but it is not always the case when it goes into closed loop. It is not always the case when it goes into closed loop. Okay. That sir has also shown in his lectures. So next part is light load. What is light load? So can anyone tell what do they mean by light load? Okay, Parvati, you also can answer. Or you could also send a message on the chat. Anything is fine. Okay. Does anyone know about the transformer efficiency curve? What happens in a transformer efficiency curve is this is your power output and this is your efficiency. So your efficiency will rise, 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 come to one sweet spot, and then it will fall. It will fall somewhere. Okay. So at this spot, what actually happens is your switching loss or your core loss, etc., that is equal to your copper loss or your iron loss. Okay. No, 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 copper loss. Iron loss is your uh, inductor loss. So that means in a in a let us say in a practical DC to DC converter, which is the topic of this NPTEL course. You can have buck boost anything. You have mainly two types of losses. One is your conduction loss. One is your conduction loss. One is your switching frequency loss. So conduction loss depends on your current, your RMS current. Switching frequency loss primarily depends on your switching frequency. So what happens is, as your load current, that is your load current, as it reduces, or your load resistance as it increases, what happens is your conduction loss will reduce. Your conduction loss will reduce. But your switching loss will almost be the same. It almost remains the same. So your efficiency, which was what? Your P output upon P output plus P losses. This is your efficiency. This is actually your P output upon P output plus P conduction loss plus P switching loss. So as your load is reducing, what is also happening is your P output, this also is reducing. When your load current is reducing, your output power also is being reducing. So this is reducing, this also is reducing, this also is reducing. But P switching remains the same, but your P conduction also is reducing. So let us take some numbers. Let us say your output power is 98 watt. Okay. When your load was 100%. Assume that. Okay. And your P conduction loss was, let us say it was 10 watt. And your P switching loss, let us say it was 5 watt. So what is your efficiency? Can you tell me what is the efficiency? Hmm?
86.5.
Okay, 86.5, good. So this is your efficiency. Now, let us say my load has become 50%. Okay, it has become 50%. That means my output power has become 49 watt. What do you think will happen for my conduction loss? How much will it become?
One-fourth.
Yeah, because conduction loss is dependent on the square of the current. So my conduction loss will become 1/4, so it will become 2.5 watt. Okay, my conduction loss is become 2.5 watt. So now, but my switching loss remains the same. So my new loss is new neta mu, or light load. Light load, it's not exactly light load, it's quite mid load, is 49 upon 49 plus 2.5 plus 5. So how much is this?
Same only. Same only.
Coming same.
86.7.
86.7.
Sir, in the previous case also it was 86.7 something.
Oh, this is very odd. For sure. Because this is 98 by 108,113. And this is 49 by 56.5.
Yes, sir. It's 86.7 only.
Hmm.
Both cases 86.
This usually shouldn't happen. Okay, let me go for even much more lighter load. Let me say load is 10%. Then how much is my output power? Output power in that becomes 9.8 watt. Right? How much is my conduction loss in that case? 10% means 0.1. 0.1 square. 0.01 into 10 watt. So 1 by 10 square into 10. So my conduction loss becomes 0.1 watt. Okay. But my switching loss is 5 watt. Okay. So in that case, in the light load, let us see the efficiency. Output power is 9.8. Output power again is 9.8. Conduction loss is 0.1. But my switching loss remains 5. In this case, what is my efficiency?
65.7.
Yes, 65.7. Okay. So the efficiency has reduced drastically. So what happens is, like as you guys also found something which I didn't perceive. This is your load. This is your load. This is your efficiency. Okay. It may be sort of, straight. For some load, it will be straight. It will be straight. Afterwards, what happens? It starts dipping. It starts dipping. And this is not what we want. This is not desirable. See, like in your, let us say, in your mobile, you guys use your mobile, use your computer, everything. When it is just on, when your mobile is on, you're not using it. It is operating in light load. Kind of it's operating in light load. It is not drawing lots of current. But when you're seeing a movie or you're downloading something or you're listening to music, everything what happens, that time it is, or you put it on updates, it is getting updated, etc. That time many tasks are happening at the same time. So that time it will draw lots of current. So that is heavy load. That is full load. Okay. So during light load, what happens? The current is very low. And when the current is very low, the efficiency is low. And this is very severe in all your phones and all these things, in all your processors, etc. This is very severe. So what you have to do in that case is you have to reduce your switching frequency. If you reduce your switching frequency, then your switching loss also will reduce at the same time. Okay. Because at light load, usually what happens is, let us say this is your inductor current. It would be somewhat like this. It would be somewhat like this. Okay. Suppose this is your inductor current. So in these cases, so what happens is part of the time it is transferring power from your input to your load. Power is being transferred from your input to your load. And part of the time, power is being transferred from your load to your input. Okay, that's why the current is going negative. The power flow, like most of the power, or like some part of the power, like let us say 60% of the power is going from the input to the load, and 40% of the power is being recycled back from the load to the source. That's why your current has gone low, it has gone negative, etc. And when this is happening, what is happening? There are these resistors are there, like the high resistors are there. The switching losses are there. Those are unnecessary. You don't need those losses. So what people prefer to do is they prefer to operate in DCM. And then if you just give one long charge, long amount of time, then in this case, you're injecting lots of energy. You're injecting quite a bit, or injecting energy for some part, and then you're not injecting energy. Then you're again injecting energy, and then you're not injecting energy. Okay, and what will happen is your output voltage will be something like this. Your output voltage, if it's a buck converter, it will could be like this, and then it would just decay, and again it will rise for some time, and then again it will decay. But it will be within your limits. It will be within the limits specified. It will be within the limits. Okay. So you don't need to pump in lots of energy. You don't need to continuously, here what is happening, you're continuously pumping in energy and it is coming back, going back here and there. You're doing it all the time. Like you're running it at a speed which is not necessary. You can run it at a lower speed. So what happens in light load is we prefer to run it at a lower speed, at a lower switching frequency. Okay. So the objective of light load control techniques is that you want to reduce your switching frequency. And sir had shown, okay, sir had shown like this constant on-time control. This is known as constant on-time control. This is very useful because your switching frequency is proportional to your load current. So if your load current reduces in light load, your switching frequency also will reduce. So that is the advantage of constant on-time control. This is one of the reasons why it is used a lot. Okay, one of the reasons why it is used a lot. Anything you have doubts from all these which I have taught? Any questions? Okay. Then I think we can start with some of the questions. Okay. Let us say these are not numerical. This one is not a numerical question. This is just to test your understanding. Okay. So can you tell me what are true, what are false for the following? Okay, let me just check if MATLAB simulation is there. Okay. So this is my boost converter peak control code which I have written. Okay, let me just check it once. Let it run. No. This running. Till then we can check this question. So any ideas? Divya, Parvati, Arun. We can let the ladies go first. So what do you think? What is right or wrong? Because ladies are always right. So please tell us.
The first one is true. First one is true.
Oh, okay, correct. You are right. Then second one is you're not sure. Okay. Second one you're not sure. Then you can go to next one. C case. What do you think? Okay, so I'll give a hint. If you just see input is 12 volt, the out is 48 volt. So what should be the duty required in that case? For boost converter, input is 12 volt, output is 48 volt. What should be the duty required?
0.75.
0.75. Okay. So is that greater than 0.5 or less than 0.5?
Greater
Greater
than
than
0.5.
Greater than 0.5. Okay, so valley current mode control has instability, that is unstable issues when your duty is less than 0.5. But when your duty is greater than 0.5, valley current mode control is stable. Okay, so that's why C also is true. A is true, C is true. Now D. What do you think of D? Like you have learned about voltage mode control and current mode control, right? So there are certain benefits of current mode control. Let me, what's happened to my screen? Okay. So in current mode control, you have this. This is your reference. Then when you add a RAM compensation, it will be like this. The reference will change like this. Again, it will go like this. Okay. And your current will be something like this. It will come here, fall, come here, fall. Like this. Okay. So this is your RAM. This is your RAM. This is your original reference. And this is your inductor current. Okay. So now, when you increase this ramp, you make it more and more steep. What happens is, instead of it operating as peak current mode control, you're actually forcing it more to work like in ramp control. Like if you say, what is voltage mode control? You have this ramp like this, something like this, and you're comparing something and you're getting your gate signal, right? You're getting your gate signal like this. So this is, so what happens here is you have an artificial ramp, right? In voltage mode control, you have an artificial ramp. But in current mode control, what you're doing, you're using the natural ramp of the inductor current. You're using the natural ramp of the inductor current to generate your duty. But when you're increasing the ramp, you're adding a bit of artificial ramp that's there. And if that artificial ramp value is a lot, very much, then you can mathematically, they can show and they have proved, it is documented also, that it will slowly become like voltage mode control. That means the effect of your inductor current is lesser and more, it is due to that artificial ramp. So this artificial ramp also, it has an issue, it kind of slows down your response. It slows down your speed. So that is why slowly we are shifting to variable frequency control. Like in constant off time control, constant on time control, you don't have those subharmonic instability issues. They are not there. Okay, they are not present. Okay, so this is one point. So very high ramp compensation forces peak current mode control to operate as voltage mode control. That's true. And this subharmonic instability has negligible effect on the converter efficiency. So what do I mean by subharmonic instability? That is, you have your reference like this, and your current goes like this, then it stops off here because your time period is over, and then it will again rise like this, fall here, again your time period is over, then it will rise like this, fall off here, because again your time period is over, and it will go on. Okay, it will go on. So this is the subharmonic instability. It could be like this, it could be worse, it could be different, all that. That depends on various parameters, etc. Now, ideally how your current will look like would be like this. It would be something like this, 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 like this. This is how you want your current to be. But because of this peak current mode control or valley current mode control, because of the subharmonic instability, which is there due to that fixed frequency operation, your current ripple has increased. It is first of all not periodic, which is not good. There can be cases of EMI spectrum, etc. And the ripple is more. So losses are more. That is why it is not advisable to permit this kind of subharmonic instability. Okay. So that's why our fourth, this subharmonic instability has negligible effect on the converter's efficiency. This is false. This is not true. Okay. Now, RAM compensation requirements, ideally, it doesn't depend on the load current. Because when we, mathematically we find out and formulate how much RAM we need, that we do it independent of the load current. But when you do closed loop and you do the perfect model, everything, there might be some dependence. Okay. So any questions in this part? Or can I proceed to the next question? Okay. I'll go to the next question. So, question 2 is about variable frequency current mode control. So, now you tell me what is true, what is false. Let me know.
A is true.
Okay, good. Next.
B is false.
Okay, because constant on-time control is analogous to valley current mode. Great. Next.
C is also true.
Okay. And D?
D is also true.
Okay. Okay. So, madam, do you have anything to say? Whether any discrepancies are there?
No, sir.
Okay. Let me just say something. So, we have, so we are talking about variable frequency control. So the advantage is we are not constrained by this time duration. It is not constrained. It could adjust. It can adjust. But in this peak current mode control, valley current mode control, we are forcing it. And you have to finish your cycle within this time key. Okay, so that is the reason the subharmonic instability is not there. Sir has also shown some math why that subharmonic instability is not there. Second of all, you have constant on-time control. That is analogous to valley current mode control. And this constant on-time control, it is very useful, as Sir had mentioned, in buck converters. When your duty is very, very low, duty is very low. Like in the case study which Sir was referring for VRM application. So VRM application, that time the duty will be around 1/12 because your output is 1 volt, input is 12 volt. Okay. In such a case, peak current mode control doesn't work because the time duration which is on is very small. That is, current is like this. Current is like this. So your gate pulse is on for such a small duration. Okay, it's on for such a small duration. Okay. So we know that peak current mode control is stable for D less than 0.5. And that is being valued over here. It is valid. D is less than 0.5. But this D is very, very small. Okay, so there are various delays like this sensing delay is there. The gate driver to turn on delay is there. Okay, there are computational delays there. That's why peak current mode control is difficult. It is difficult. It's not like it's impossible, it is difficult. So what people have gone for is constant on-time current mode control. By this on-time, you can set a small on-time. It will not be affected by the noise over here, the switching noise over here, switching noise over here. It will not be affected much by that. So you know your on-time has to be fixed. You can send that amount of on-time. And if your regulation has to change your off time, this off time will get adjusted. This off time will get adjusted. Okay. That's why constant on-time control is kind of valley current mode control. It is not peak current mode control. Next is hysteresis current mode control. Now, hysteresis current mode control also is known as on-off control, right? So a common example which I teach my students is like we do this in the control lab. We have what is known as on-off controller. That is, if your signal goes below some certain value, then you turn it on. Then you turn the system on. Let us say previous years, you had what is known as those ACs and everything, where if your temperature has gone much lower than your desired value, let us say you set your temperature at 20 degrees centigrade. Let us say your temperature desired is 20 degrees centigrade, but it goes below 19 degrees centigrade. What does it mean? You have to turn on your, that means you have to turn it off. Okay, in the case of AC, you have to turn it off. And then when your temperature will rise and hit some, let us say 21 degrees centigrade, that means you have to turn on your compressor, AC, everything. So that time you will turn it on like this. Okay. Then once it again goes below 19, then you know that you don't need the compressor to work. So you again turn it off and it will rise. So this is in the case for an air conditioner system, AC system, etc. It could use in process control, all those places, everything. But in the case of a converter, it is opposite. That is, your gate signal Q, it will be high when it is on, and when it touches the peak, it will go low. Again, it will turn high here, and it will go low here. Okay, this is hysteresis control, where this will be your I valley, this is your I peak. Okay. Now, to do this, you need to have this information of your current. You need to know your current when it is reaching the peak. You need to know when it is reaching a valley. All that you need to know. For that, you need to have a very good sensing. Very good sensing you need to require. Then, there is an issue when you turn on and turn off, there will be noises. There will be these noise spikes will be there. So these noise spikes can affect your control. If the noise spike turned out to be like this, that means it turned on here, turns off here, again it will turn on. Right? It turned off here. That is, it turned off here. But because your send signal had some noise, it might again turn on over here, which is not permissible. Your switch cannot turn on off very, very fast. It cannot turn on and off very fast. Although your switch is fast, but you cannot permit it to turn on at such a fast rate, right? So that is why hysteresis current mode control, your sensing has to be very good. And you need to have certain mechanism that you should limit your switching frequency, right? Your switching frequency cannot go very high. Okay, so that is another issue in hysteresis current mode control. That is an implementation issue. Okay. Next is minimum on time is required for constant off time control. Yeah. So like what happens is you are turning on, you're turning off for a fixed duration. Then you must give some minimum time on. Like there should be some T on minimum. Okay, and then again it turns off for some fixed duration. This minimum time, why is it required, is because in a boost converter, what happens is your output voltage is falling here, and here it is rising. Again, it is falling here it is rising. So if you don't give this time for it to fall, then your voltage will just keep on building up, and then it will damage your thing. Okay, so that's why you need to give this minimum on time. There, like sir has also explained, you need to give a minimum on time for constant off time control, and in constant on time control, you must give a minimum off time. Those are practical implementation issues are there. Okay. Okay. So can you tell how to proceed with this question?
We can first calculate duty ratio.
Yeah, that's the best way. So question 3. So your VN is 12 volt. V out is 20 volt. So what is your duty in this case?
1 minus 12 by 20. So 1 minus 0.6.4.
So duty is 0.4. Okay. Your switching frequency which you desire. This is like your nominal switching frequency. Because you must understand this is constant off time control. The T off is fixed. That means your switching frequency can vary. But when you're designing, you consider some nominal switching frequency you're considering. And that has been decided as 200 kilohertz. Okay. So that means under nominal condition, your T off will be equal to your 1 minus D into T. Right? How much is that? That will be 0.6 upon 200 into 10 to the power 3.
T is 5 microsecond. So 3 microsecond.
Oh, yes, yes. So it is 3 microsecond. So this is your off time which you got. You have got this off time. Now, they are saying what is the required IREF. Okay. So you have your IREF over here. Current is going like this. There's this fixed T off. Again, it will hit. And again, you'll have fixed T off. Right? So what is this IREF which you need? First of all, this is your delta IL. Right? And so this is your peak. And you have what is known as your IL average. So you have to find your IL average. So how do you find the IL average?
I0 by 1 minus D.
Okay. So you're in a boost converter. So this is a boost converter. They're giving you output is 100 watt. Your V out is 20 volt. Your I out is how much?
Five ampere.
So your I output is 5 ampere because it is P out by V out. Okay. This is your output current. Now, in a boost converter, your IL average is equal to I out upon 1 minus D. This comes from output capacitor charge balance. Okay, so what is your IL average in this case then? IL average is equal to 5 upon 1 minus 0.4. So how much is that?
Eight point 33.
3.3. 3 point.
8.33.
8 point.
That will be 8.33 ampere. Now, we have to find what is the delta IL. So can you tell me how will I find delta IL?
V minus V0 by L.
Delta L,
Is it correct?
again? Hello? You can tell. Don't worry. How will I find out delta L? So delta IL is given by the slope. Okay. So what is the falling slope?
Vn minus V0 by L.
Yes. So delta IL actually is V in minus V0 by L into T off. But you must remember V in is less than V output. That's why you must have a minus sign. You must have a minus sign. So what will be this value then? What is your delta IL then? This minus of 12 minus 20 UL is 3.3 microhenry. What is the T off you got? You got T off to be 3 microsecond. So what is the value?
7.27.
Delta I comes out to be 7.27 ampere.
Yes, sir.
Yes.
7.2.
Yes, correct. 7.27 ampere. Because this gets cancelled. This becomes 8. 3 by 3.3. Okay, 7.27 ampere. So that means your I peak, that will be equal to IL average plus delta IL by 2. Okay, your IL average was 8.333. Delta IL is 7.27 by 2. So how much is this?
11.97.
11.97 ampere. Okay, any doubts in this? Okay. So we proceed to the next question. Hysteresis current mode control. So you have a boost converter operating under hysteresis current mode control. These are some expression input, output, inductance, etc. You find the expression
Sir,
for
one doubt. In
yes,
the
yes.
previous question, can we
Mhm.
directly take that F desired as the switching frequency, or is there any other possibility?
When you're designing, you can take it. You can take it for making it simple. But you're talking of which part actually? Because here we have not considered your switching frequency in the
Uh,
current triple calculation. Average also we have not
because
considered switching frequency. That's it.
that 3 microsecond was calculated based on 200 kilohertz.
Yeah. See, because this is your design criteria. You have been told to design it in such a way that your nominal switching frequency is 200 kilohertz. If that is provided to you, that is in your steady state, you have this, then your off time, you can give it directly through this expression. Okay. Because your duty is still there. Like the concept of duty is still there in variable frequency as well, right? That you need it to be on for some duration and off for some other duration. That is, if your switching frequency was 100 kilohertz or 200 kilohertz or 400 kilohertz also, for this input of 12 to output of 20 volt, your duty should be the same. It is not dependent on switching frequency. Your duty will remain the same, but your ripple, your voltage ripple, current ripple, they depend on your switching frequency. Okay, so your duty is correct. Your duty is independent of your switching frequency. So you got your duty. There's no problem in that. Next is they told you need this switching frequency. So because you need this switching frequency, that's how you can calculate the off time. There could be another case where they tell you to find the off time by considering the ripple. That is, they say that the ripple should be this much. So now you design the off time, and this is the inductance, etc. In that case, it's a different scenario. Okay.
Okay, sir. Understood.
Okay. So now hysteresis current mode control. Now what is hysteresis current mode control? Okay, that you all know. By now you understand it well. But what I am looking for you to do is, you have your peak, you have your value, right? For this time, it has a positive slope m1. This time it has a negative slope minus m2. Again it has m1. Again it has minus m2. Okay. This is your delta IH. This is your delta IH. So now you have to find what is your time period, what is your switching frequency. How will you get that?
Delta IH by M1 plus delta IH by M2 will give us the total time period.
Okay. So this T on, and T off. Your T on, as he said, it is delta IH by M1, and T off is delta IH by M2. So your T is equal to T on plus T off. So it is equal to delta IH by M1 plus delta IH by M2. So what does your T become? Delta IH into M1 plus M2 upon M1 into M2. So your switching frequency becomes equal to M1 into M2 upon delta IH into M1 plus M2. Now, for a boost converter, what is M1 and what is M2?
M1 is V in by L. M2 is V out minus V in by L.
M1 is V in by L, M2 is V output minus V in by L, right? So you put those over here, what will you get? Did you get any good expression?
To V by V0 L delta IH.
Louder, please. It is V0 minus Vn into
In
Vn, okay.
divided by V0 L delta IH.
Okay, correct. V0 into L into delta H. Yes, correct, good. Okay, so this is the expression for switching frequency. Now, let us go to our question. So here we are given Vn is 12, V output is 20, inductance is 3.3 microhenry, and delta IL is 5 ampere. So now we have to calculate. So what do we have? This is 20 minus 12 into 12. V output is 20 into L is 3.3 microhenry. And your delta IH is 5 ampere. So how much is your FSW? Okay, what is the switching frequency? Can you calculate and let me know?
Okay. 290 kilohertz.
290 kilohertz. Okay, this is the value. Okay. Now we want to know what is the required IREF for peak current hysteresis control. That means you have to find this peak value. You again have to find the peak value. So how will you do that?
IL average plus delta is by 2.
Yes. So your peak is equal to your IL average plus your delta IL by 2. Okay, your IL average is what? IL average is you had calculated earlier 8.333. Delta IL is 5, so 5 by 2. So this is the value which you have to get. Because your delta IL is equal to delta IH. Right? And we have considered the same condition. So IL average was 8.333 earlier, which you had computed.
Sir, can you show me the question?
Okay. Just one minute. This is the question. Do you have any doubts with it? Any doubts in the question or something?
Okay.
Sorry?
No, sir, just to give the question.
Okay, fine. Okay. So this is how you get. So you get your IEL average will be 8.33 plus 2.5 would be how much?
10.83.
Correct. 10.833 ampere. So we have to set this value. We have to set this value by our, when we will actually implement, we will give this value. Okay. You have to give it through your FPGA or microcontroller. You'll have to use through a DAC, you generate this, etc. This is the way it works. This is the way it's practically implemented. That's why I wanted you to calculate those values so that you can understand. Okay, and in a practical case, like you're not comparing current versus current. You cannot do that. You're actually comparing a voltage. That is, your reference will be some voltage, and this signal also will be actual sense signal. This is a sense signal. So this sense signal is a scale down factor of your current. Okay. And this also I peak will be a Bref. Not exactly Bref, doesn't sound correct. Your V peak, which you will set from your through a DAC, you will send it out something. But it should be a voltage. Okay. So this is for practical case. Just giving you some idea. So now let's go to the next question. This is Schmitt trigger. Okay. So can you draw, like, what do you know? What do you mean by Schmitt trigger? Does anyone have any idea what is a Schmitt trigger, what it does? It's a very odd name, everything.
It is a comparator with a hysteresis.
Okay, comparator with hysteresis. Okay. So you have a op-amp. Okay. So this is the positive terminal. This is your V output. This is your signal B in. This is your, let us say, your Rx, Ry. And this is your Rm. Okay, this is Rm is not required. And this is your ground. Okay. This is your plus V supply minus V supply. Okay. This is your Schmitt trigger. So now, this is, if you will notice, it is configured in positive feedback. So when it's in positive feedback, what could be the possible output voltage values? What do you think? The output voltage will be how much? It will be 0.5 V supply. It will be 0. It will be minus V supply. What will be the value?
Positive and negative V saturation, V supply.
Okay. So it will be saturated. It will either be at plus V supply or it will be at minus V supply. Okay. So how do you analyze this? Like this was I'd done a previous course, electrical measurement and electronic instrumentation. So where this was also considered. So how the professor taught was, we will assume that my output is equal to plus V supply. Assume this my output is plus V supply. Okay. Then this is your V plus. So what will be your V plus? Your V plus will be equal to Ry upon Ry plus Rx into plus V supply. This is your V plus. So now your output is plus V supply. Your V plus also is plus V supply. So what you are looking for the point, the transition point, when it goes from positive to negative. You're looking for that point. Some volt at this input voltage, my output will go from plus V supply to minus V supply. So what would be that point? What point do you think it will be? And at that time, you remember your V positive is equal to Ry upon Ry plus Rx into plus V supply. So what should happen? Suppose your input is changing, it could be ramp, it could be sawtooth, anything. But at some particular voltage, it will transition from plus V supply to minus V supply. What do you think?
When the differential input to the op-amp becomes positive, output will go to negative V sat. That is when V in is less than V plus.
No, if your V in is less than V plus, then the effective signal over here is positive. Then output also should still be positive, right? Because it is plus minus of that. And you know op-amp, what is your op-amp output? This gain into your V plus minus V minus. Ideal op-amp, everything. So what should I do then?
It should be reverse. V in should be more than.
Yes. So this happens when your V in becomes greater than V plus. At that case, your output will become negative. So if you have, let us say, this is your plus V supply. And this is your minus V supply. Okay. Assume you have some signal, let us say a sine wave. Going like this, like this. Okay, it's a very distorted sine wave. Ignore it. So, what will be the output of my comparator? What will be my V output? So, this blue is my input, right? When my input goes above this point, okay, this is my plus V supply. So, this is my plus V supply minus V supply, right? And there will be some point which is known as my V threshold plus, let us say V threshold upper and V threshold lower. That is just a scaled down version of your V supply. It's a scaled down version of your V supply. So at the instance when it crosses this point, this point, this point, this point, there certain things can happen. So we have told that my output, assume it is plus, when it crosses this point, when it crosses this V supply into a scaled down factor of that, my output will go negative. So in that case, what will happen is it will go negative. It will go negative. And your input is greater than this BTH up, it is greater. It becomes less than that also. Still, your output will still be negative. Then when it goes below this point, only when it goes below this point, then it will become positive. Then it will remain positive. Even though it goes above this point also, it's fine. When it goes to this point, then it will go negative. And so on. Okay, thus it will get repeated. Okay. So, this is difficult to understand. Let me open a simulation. That will be easier. Let's say. So this one I'm simulated in LTSpice. Okay, this is LTSpice, right? Let us check this. Okay. Let me change this. Copy it and keep it somewhere. Achha, by the way, there's a link to my channel. So these recordings will be uploaded on this channel. Okay, the recording of this meeting. So you can access it. Okay. So let me convert this into a sine wave. This may DC offset 0, amplitude 5, frequency 1 kilohertz. These things are not required. Okay. Let me run it. To time, I put to increase the time. Let me increase the frequency instead. Okay, so this is the one. Okay. So let me plot this signal. So this VN001 is my V positive. Okay, this is my V positive. I think this will be better if this is over here. So when my this V positive is a scaled version of my V output. If my V output is 12, this is a scaled down version of that. Okay, it's a scaled down version of it. So now it's a scaled down version of it. That is, the red one is the voltage at this point, at the positive terminal. It's a scaled down version of my actual V output. Now, when my input tries to go above this value, okay, above this value, then my output will fall. Okay, it will fall. And then when my input signal tries to go below this value, then my output will rise. So there is a band. There is a band in which it will operate, and that depends on these resistors, 40K, 10K, which we have considered here, and other things. Okay. So this is the inverting Schmitt trigger circuit. So any doubts in this?
No, sir.
Okay. So what I've asked in the question is, what will be the average output of the Schmitt trigger if a symmetrical triangular wave of peak to peak VM is applied at the input? Okay. So I want to apply a triangular wave. So let me go over here. Change it. This I have to change to this graph. This is square wave. Okay. For school. Okay. So this is the case. So I have this triangular wave. I have this triangular wave over here. So when it crosses this point, it goes low. When it goes below this point, it goes high. So if you will see this wave, what do you think is the average value of this V output wave? How much is it?
It's 0.
Yeah, it is 0. The average value is 0. This is because I'm using what is known as a triangular wave. But if I convert this triangular wave into this sawtooth wave, right? Then that changes it. Like it is on for more time, it is off for less time. On for more time, off for less time. Okay, depending on that, the average value will change. Okay, so you can check this. You can also simulate in LTSpice. LTSpice is very, it's a free web. It's a free software also. You can learn how to do all these circuits as well. Okay. So this was question 5. Let's proceed to question 6. So question 6 is about light load control. What are the important
Sir,
light
one doubt.
basics? Tell. Okay.
Sir, non-inverting Schmitt trigger means we have to connect the input to non-inverting terminal, right?
Yeah. Yes. Correct. Yeah. We'll have to connect it there. Let me see if I can save it. Rectify. Non-inverting Schmitt trigger. How? This is the way. Can you see it?
Yes, sir. Yes.
The negative terminal is grounded. So always in this Schmitt trigger circuit, you will have positive feedback. So your output will be connected to the positive terminal. And it will proceed like this. Simulate this also and see. This is my input. This is my output. Where transitions are at these points. It's transition. It's point this point. Input, this is my output. So the point at which it will transition is determined by these resistors. So because this 60K and 30K, it will transition, let us say, the supply is 12. So it will transition around 12 by 9 into 6. It's going transitioning around 3 volt. Around 3 and -3 it is changing. In the non-inverting case, the formula is some 1 plus R1 by R2 or something is there for the non-inverting case. For the inverting case, it is just minus R2 by R1 and all. But in the non-inverting case, it becomes a little bit complicated. 1 plus R1 by R2, something is there. But it's like the same thing. So in this non-inverting case, when your input is increasing, your output will increase. And when your input reduces, falls below some value, your output will fall. Okay, but in the case of the inverting case, when your input is trying to rise, your output will fall. And when your input is trying to fall, your output will turn on. Okay, so that's why it is one is non-inverting, one is inverting. Okay, so we'll go further. So can you tell what statements are true about light load control?
Option B is correct.
Okay, that we saw it the hard way, for example. Then
C is also correct.
okay, good.
The others I am not clear. Sir, please explain.
Yeah, ma'am can explain. Ma'am, can you let us know what do you think?
No, sir, I don't have any idea. Please.
Acha, you have not introduced yourself. Arun has told me he's from NIT Calicut. You're from which college? Or what are you teaching or something?
BIT College, Chennai.
In which
I'm a
college?
research scholar. BIT Chennai. Vellore
Okay.
Institute of Technology. Chennai.
Oh, BIT Chennai. Okay. Oh,
Main branch is in Bangalore,
okay. But you're in
Chennai
the
branch.
okay.
I'm a research scholar
Acha, in which department?
and electrical department.
Okay. Good. Nice. So actually, I am also from Chennai. So my
Okay.
grandfather is there and everything. So I don't know much about Chennai. I just go to his place, everything. So that way, yeah. Okay. So like, why have you taken this course as such?
I'm doing research work on power converters actually,
Okay.
and some control SMPS I would like to learn.
Okay. Switch on
Uh,
possible. Yes.
so related to that, I took this one.
Okay. So this is like part of your credits, or is it like out of your self-interest you're doing?
Yes, it's part of my credit.
Okay.
This semester, this is my second semester, and
Uh-huh.
I've taken one NPTEL course and one MTech compulsory course and one self-study.
Okay.
So this is my NPTEL course.
And in the previous semester, which NPTEL course you do?
Previous semester, it was like mandatory courses, 3 mandatory courses. That is general for all the branches.
Okay.
That is research methodology, then research ethics, and English for learners, like that.
Oh.
So that was mandatory for all the branches. From this semester only, we have to concentrate on our particular subject.
Okay.
Um,
Yeah. Good.
So I'm just learning, sir.
Yeah.
I'm just learning everything. I can see that all the other others are very advanced. I am just learning process. I just completed my literature survey and like that, just identified my area of research.
Okay. So
So
what is your area of research like? Unless it's secret, you cannot tell
DC.
us.
No, nothing
Okay,
in a
DC.
secret. I'm doing in DC boost converter.
Oh.
Boost
Okay.
converter.
Then this
Uh,
is very useful for you then. Very useful.
yes, sir.
Uh,
But academically, I'm a little bit. I have a lag of little 2-3 years,
okay.
so I'm slowly picking up only.
Uh-huh. Yeah.
Uh,
Don't worry. This course actually is very difficult. I'll admit this is very difficult. There's so many things I
Yes, sir.
used.
By seeing the question itself, I am worried.
Okay.
Assignment questions. That's why I came for classes,
Okay.
interactive classes.
Yeah. Assignments also are difficult. I admit it's quite difficult. Yeah. Yeah, let's see. But are you getting the what you say? When you're submitting the assignment, are you getting the result? Like how much your grade you're getting in that? Like for week one?
Get hardly I got 60% only.
Okay. Yeah. Anyway, we are like I and Teja are trying to make the questions similar to the assignment questions. We are trying.
Uh,
So like
okay.
we are supposed to make our own questions. In the
Okay.
like I used to teach other NPTEL courses, everything. So what we had to do in those courses were we had to teach the previous year assignment questions. So
Okay.
those would be like very aligned everything. Now in our
Oh,
case, we have to somewhat come up with our own questions and do. So
okay.
it's a bit difficult for us also. Like that. So yeah,
Okay.
we are trying.
First 2-3 weeks, I missed that videos. I mean, the interactive sessions, but I
Okay.
have to check the YouTube channels.
Mhm.
And without that, only I wrote assignments. So from this week, 4th week only, I'm referring to the
Mhm.
practice session.
Yeah. Like interactive session is designed for you all to
Ah,
ask actually. Yeah. So we
yes, sir. That's very useful for me, a learner like me.
don't worry. Okay. So for light load control, so constant downtime control is widely used. So PFM actually is pulse frequency modulation. pulse frequency modulation. So what happens is you're changing the frequency, which is what is happening in your constant on-time control, right? As I told, that the frequencies change depending on your load current, and so it is reducing your frequency, and so it reduces your switching loss. Second is, as the load current reduces, the switching losses dominate the overall losses. That is true. We did it through an example. Now, PSM and burst mode control suffer from non-monotonic spectrum. Okay, so in this, what happens is, let us say, like in normal PWM control, how is it? Your current is like this, right? This is your current. It has a time period T, which is 1 upon FSW, which is switching frequency. So when you plot your FFT, you will have a DC component, and you will have a switching frequency component, and you have 3 FSW, something or not, it will go. It will be the odd harmonics, it will go. Okay. But what happens in burst mode control? Let us say burst mode control or PSM control. What happens is, it will be on for some time, off, like this, it will be there. It will turn on, off, like this, it will be there. And again turn on. What might happen is this time T1, like if this is time T1 and if this is time T1, then your spectrum will be what? It will have a DC component, and you will have a FSW1, 3 FSW1. You will have something like that. You will have pi FSW1. Okay, this is your harmonic spectrum. But in most cases, this will be T2. Your T1 will not be equal to T2. Then what will happen? You may have one spectrum here. You may have another spectrum here. It will be like this. It would not be uniform. It would not be uniform. Okay. This thing even I'll have to check by checking the spectrum, everything. But in the case of PWM, you have a fixed thing. It will keep on going down. It will keep on reducing. It is keeping on reducing. But in this case, there might be a scenario where at a higher frequency, your spectrum content might be more or less. It is not uniform. It is not like consistently reducing. Okay. So that is why burst mode and PSM don't have a constant switching frequency. And even in steady state, what will happen, that frequency sometimes is high, sometimes is low. That's why they suffer from the non-monotonic spectrum. Okay. Next, final question is, light load control is usually brought about by dual mode controllers. So that is in most cases, you can consider that. In high load, we could operate in PWM control. And in light load, we can operate in pulse frequency modulation or constant on-time control or PSM control. That is in a light load control technique we will use. Okay. So then we have to demarcate. If the load current is so much, that means it is in high load. I'll operate in pulse width modulation. If the load current has reduced further, I will go into light load control technique. So that is why it is known as dual mode controller. Okay. So any doubts in this part? Okay, I'll proceed to the next question then. So we'll do constant on-time current mode control. Okay. So now, okay. So you have what is known as constant on-time control. Okay. This has those, those good concepts that your switching frequency is proportional to your load current. This happens only in DCM, only when it operates in DCM. If you're working your constant on-time control in CCM mode of operation, then it will not have this feature that your switching frequency is directly proportional to load current. It will not have that feature. Okay, that's one point. They are saying constant on-time current mode control with VIN is 12 volt. Okay, let us write it down. VIN is 12 volt. V output is 1 volt. Okay. Your output power is 20 watt. Output power is 20 watt. Your inductance is 220 nanohenry, right? And your capacitor peak current is 5 ampere. Okay. Your capacitor peak current is 5 ampere. So these are things. And this is a buck converter. Okay, this is a buck converter. So now, what do we have? In a buck converter, we have an input here like this. We have a switch here like this. Another switch here like this. We have your inductor. We have your capacitor. And this is your load. Right? So this is a current to the capacitor. And this is a current to the inductor. Right? And this is your I output. So what we usually consider is, let us say this is your inductor current. This is your inductor current. This is your average inductor current is equal to your load current in the case of a buck converter. So the remaining, your delta IL is actually your capacitor current. So what they have told is the peak capacitor current is 5 ampere. So indirectly, what's the trick of the question is they are saying that your current ripple is 5 ampere. Okay, they're indirectly saying your current ripple is 5 ampere. Okay. This is done. Okay, so what's the question about constant on-time control? What is the required on-time? What is the on-time which we require? So you have to find this on-time which you need.
Sir, why is it delta IL equal to IC?
Okay, because your IL is what? IC plus I naught, right? Now your I naught, we assume it to be constant. We assume it to be flat. Because what do we want? We want your output to be regulated, be constant, right? So this
Yes,
IL,
sir.
this IL has two parts. Your IL is IC plus I naught. So it is actually equal to your IL average plus your delta IL part plus your ripple part. Okay. And this is your I naught plus your IC. So this and this get cancelled. So your IC peak to peak is your current ripple. This is true for buck converter. This is true for buck converter. And this also tells us why buck converters are used for, supplying all these converters and everything is because.
Sir, then IC delta IL is 5 or 10?
Oh, your delta IL is 5. 5, right?
Because capacitor current peak is 5 ampere. So peak is delta IL by 2.
Sorry. So this is your this. Let me drop this part. Your capacitor current is actually like this. Draw a different color. Yes, this is your capacitor current. Correct. So the peak they told is 5 ampere. So peak actually is delta IL by 2. Okay. So the IC peak is actually equal to delta IL by 2. So your delta IL is 5 into 2, 10 ampere. Sorry, you're right. Yeah. Okay. So this one thing where I messed up. So delta IL is actually 10 ampere. All right. Then what was the question? Constant on time. What is your required on time? So your delta L is 10 ampere and your output they gave is 20 watt, right? And your V output is equal to 1 volt. So your I output is equal to 20 ampere. 20 watt by 1 volt, that is 20 ampere. That is your I output. Now, we want to find your delta L. Delta L, how it is given by in a buck converter, it is V in minus V output by L into your T on, right? So delta L you found out to be 10, V in is 12, V output is 1, L is 220 into 10 to the power minus 9. This is your T on. So from here you can calculate T on. Okay, can you calculate and tell me how much is it?
Point 0.2 microsecond.
So T on comes out to be 0.2 microsecond. Okay. Very good. Any doubts in this part? Okay, next is you have to find the load resistance for CRM operation. That means your load current will reduce, your load resistance will increase. You'll be finding the case when the current will be like this. Exactly, it starts at 0. This is your CRM operation. Okay, this also you can check. Okay. So the meeting will end. If you have any doubts, you can ask me. I can start the meeting again. Or if there are no doubts, we can end the meeting today.
Okay, sir.
Okay. Thank you for joining. Good night.